So let's see what are the steps to apply this Gauss law, right? So these steps, as I told you, we can apply it to any surface. So first thing is, define the type of charge density. What is the meaning of it? Depending on the nature of charge distribution that you have, you need to define the charge density for it. Okay. So what I'll do is, I will take an example that we already know, right, for which we already know the result, and then apply these steps and show you. So parallelly, I'll be finding the electric field due to a point charge. So what is the electric field due to a point charge at a distance r from it? It is kq divided by r square. Right? This is a known result, but this, the kq by r square, we derived it using Coulomb's law. Now we will derive it using Gauss law. So first thing, due to a point charge, first thing is, I have a point charge, right? So is there any type of charge density you can define for this? No, because it is just a point charge. Second is, consider a Gaussian surface around the charge distribution, right? And ensure it passes through the point where the field is to be calculated. Suppose I am interested to calculate the field at this particular point P. Now I need to consider a Gaussian surface which is symmetrical to this. So with respect to a point, what is the symmetric shape that you can get? Meaning, this point P could have been here at a distance r, or it could have been here at a distance r, or it could have been here at a distance r. Like this, it can be anywhere. If you join all these points, what is the shape you are going to get? You get a circle. But this point can be here, this point can be at the back of the board also, meaning it should be a sphere. Am I clear? So one more important point, what is that we need to consider? You need to ensure that the Gaussian surface is always passing through the point where the field is to be calculated. So you need to take the Gaussian surface in this case to be a sphere of radius r. Third point, we need to consider a small area dA on the Gaussian surface. Suppose the sphere is like this, right? If I take this knuckle, for instance, right, this will be a small area that is present on the sphere. So what I'll do is, I'll consider a small area here, and I'll assign the value to it as dA. Am I clear with the third step? Right. And what is the, oh, so okay, dA, and assign direction to it. So with respect to the aerial vector, what is the direction? It is always in the radially, yesterday I told you, it is always in the radially outward direction, right? Meaning I should take it like this. So that is the direction of aerial vector. So first step, second step, third step is over. Fourth step is, find the direction of electric field through the small area dA that we have considered in step number 3. So due to this charge distribution, due to the positive charge, what is going to be the direction of electric field through this small area dA? So when you draw the field lines for it, how is it going to look like? It is going to be outward like this, among which one such electric field line will pass through this, right, which I call it as E. Remember, E and this dA are parallel to each other. E and dA are parallel to each other. Now what you are supposed to do is, find the total charge enclosed in the Gaussian surface. What is the total charge enclosed by the Gaussian surface? Only one charge, Q. So is it clear till the fourth step? Fifth step, right? The next two steps, what is it? Apply the surface integral of E dot dA is equal to Q divided by epsilon naught, solve for the electric field. So we are almost at the end. So what is that I am supposed to do? The surface integral of E vector dot dA vector is equal to the charge enclosed divided by epsilon naught. What did I apply here? Basically, Gauss law. The total electric flux is equal to 1 by epsilon naught times Q. Right? What is the angle between E vector and dA vector? 0. right? When it is going to be 0, then can I write this as E into dA is equal to Q divided by epsilon naught, right? The value of electric field is constant at a given distance. So if I take this dA anywhere on the surface, the value of electric field would have been a constant. So I need to take that constant outside. So what will I write it as? E into the surface integral of dA is equal to Q divided by epsilon naught. Makes sense? You know, right? In differentiation integration, you can take out the constants, right? Now see, E is okay. What is the surface integral of this dA? This is what we need to understand. On the three-dimensional shape, on the sphere, if you take all such dAs and add it, integration is basically adding. On that surface, if you take all such dAs and add it, what is it you're going to get? You will get the bigger area. What is that area? It is going to be the surface area of the sphere. And what is the surface area of a sphere? 4 pi r square. Where did I keep? So I'll write it in the next page. So E into, I'll write this again, E into integral of dA is equal to Q divided by epsilon naught. E into, what is going to be the surface area? 4 pi. What should be the value of R I should take? That is the radius of the Gaussian surface itself. So which is going to be small r square is equal to Q divided by epsilon naught. So what is the value of electric field? Q divided by this 4 pi and epsilon naught I'll combine. This r square I'll write it separately. You're able to understand. It's the same thing that we derived in a different way, right? So this example I took only for you to understand the steps. Is it clear? Right? No. Which one? This step? Huh? You didn't understand why that. This one you are clear? Huh? Yeah. So if you take a sphere, you took the dA on that sphere, right? Like that, how many such dAs will be there? Infinite. If you add all those dAs, so if you integrate all such dAs, what will you get? Meaning, if you take a sphere, okay, let's say I give you a brush. With a brush, you are placing a dot on top. You dip it in a paint, put one dot, you get dA. Similarly, you put another dot, you will get dA. Like this, if you put infinite number of dots, what is the area you are covering? The outer surface, no, of the sphere, which is 4 pi r square. That is the reason I took 4 pi r square. Right? So this is going to be the answer. Please make a note of it. So when you're writing, in your book also, I would suggest write it in the landscape mode. Turn your book like this, and like write it the way I wrote it.